Okay, well, it's been a minute since the last time I did an actual physics lecture here. I did finally upload some tutorials recently on data analysis using Octave, Python, and uh, also just spreadsheet programs. But it's time to finally talk about actual physics again after a year and a half. So I think I already did a little update where I said I'm going to make these into sort of a circular buffer. So if I paint myself into a corner, I can always just plan to loop around and replace things later. But that also means I'm trying to make things somewhat modular and universal, uh, and with an emphasis on my particular philosophy, which is to really bring together theory and experiment to understand how to use mathematical tools properly, but to use them to understand, like, the real world and not some idealization thereof. And I really want to do that, want to emphasize the ability to take data yourself and analyze it yourself and then perform calculations to model that data yourself, or perform calculations to understand hypothetical situations yourself. So I'll always make my code and whatnot available. So, but let's go back to where we left off, which was talking about a little bit of calculus, and started talking about derivatives by talking about the difference between something called instantaneous and average velocity. So remember, start out with this example of we want to go from point A to point B, say house to work, or any two places in space, and say we measure distance in terms of some unit, and the way that what that of course means is that we take something like this, a ruler that let me find this. Is that the centimeter side? Yes, this is the centimeter side, and we say, okay, this has some fixed length. Oh, this has 2-inch sides. How about that? Well, centimeters would be better, but I guess I have on hand what I have on hand here. And we say, this unit of measurement fits. We can fit so many copies of this reference into the space in between 2 points, and therefore it's however many instances fits. But it's not going to be an integer, right? Because the say the just like the length of this paper, right, is going to be more, or is going to be less even than 12 inches of a ruler, because standard paper here in the US is 8.5 by 11. So see, the ruler sticks out past the end. So we say it's less than 1 foot, and say we want to measure some huge distance, like say want to measure from here to the grocery store or whatever, put this little ruler however many gajillion times, say a mile-ish. So that's going to be, well, it's not going to be gajillion, it's going to be on the order of 5,000, because there's 5,280 feet in a mile. What a delightful number to have memorized. I'm always a little bit of an apologist for imperial units, even though, to be honest, they're atrocious. But if all you ever use is metric units, you'll never understand how to convert between different systems of measure, and you'll forget how the measurement process actually works. Versus if you're forced to go back and forth between imperial units and metric units, it's a nuisance, and you wish you could just use metric units all the time, but you at least get this fringe benefit of, you understand the idea of units a little bit better, in my opinion. But you can count up how many copies of some reference length fit in a distance, and if it's, if you need some finer resolution, you can go to a shorter reference length, and there's different, geometric techniques for constructing a shorter ruler that is, as close to precisely as possible to, half of a length or something like that. And then we have something similar in time, but it's a little bit more challenging, right? Where you have something like a pendulum, where it takes the same amount of time every time it swings back and forth, and we can count how many times it does that. And historically, it was easier to measure distance with finer resolution than it was with time, right? Because, I mean, it took people a while to even get to the point of something like pendulums, and usually you have to use something like a day. And even if you have a sundial, that maybe gets you a resolution of, within, say, half an hour at best. So not very good. So, but we prefer to use things like kilometers and seconds that we're accustomed to today, but, it ain't so easy, right? And so now consider, though, like I was saying, if you get from point A to point B in some fixed amount of time, I was very fixated on this idea of Zeno's paradox, that, how do you deal with the fact that as you zoom further and further in time, you have shorter and shorter distances covered, right? And, is there a limit to how small of a distance you could in principle measure, and how small a time you could in principle measure? And there's a critical assumption we're going to start making going forward, which is there is no theoretical limit, even if there is a practical one. And again, make an intelligent combination of theory and experiment. We want to be aware that there very much is a practical limit, and we're going to discuss that a little bit more in a minute. But there is no theoretical limit. There's no equivalent of a frame rate or a pixel size for the universe. And we don't know that for sure, but every experiment we've ever done has indicated that that's the case so far. And so let's think about it on a scale where this is only sort of an issue, though, which is, let's go back to thinking about, representing this process of going from start to finish in some period of time by graphing, plot points of, position on the vertical versus time on the horizontal here. And let's, plot some actual data points, and then do some mathematical modeling. Because remember, previously I showed you this data from me driving, which is approximated by a constant, just driving at a constant speed, represented by that straight line, and then we represented that mathematically with just an actual, y equals mx plus b, or, a times x straight line. So let's go back over to the data, but now in computerized analysis, which I did the tutorials on. So you can either just follow along with what I'm showing, or you can, and this is much preferable, perform the analysis yourself using my code and the data, and sort of pick it apart on your own. Okay, so here's the data from me driving again, with distance plotted vertically on this upper plot, and the speedometer readings plotted vertically on this lower plot, and time horizontally on both plots. And these plots are being generated in the program MATLAB, they're being generated in the program Octave, which is a free and open source equivalent to MATLAB, although the same code will generally run in either, with some exceptions, with features that are not necessarily available in Octave. But I quite like Octave. I used MATLAB all through graduate school, and now I use Octave for these projects, and I strongly recommend learning that. Or I did tutorials in explaining how to generate these plots in Octave, but I also did a tutorial showing how to generate them using the programming language Python, or how to just generate them using a spreadsheet program, or you could always just do it by hand using a piece of graph paper. So, but notice how these data points lie on something that is vaguely like a straight line. And so, like I said, we're trying to come up with ways to understand reality using mathematical models, always being aware of the fact that our models are approximations, but nonetheless learning to leverage them, because, well, reality is complicated, and if we can come up with ways to understand it, we can do some pretty nifty stuff. So, what if we just drew a straight line through this data, and, well, what if we just drew it from start point to end point? Well, that's not too shabby. We get, average of 35 miles an hour. So this, y equals mx plus b is a straight line. So, in this case, it starts at 0. So it's just 35 times time. which gets us to, 1.1 miles in 113.5 seconds. And then we can, conversely, we can say, okay, well, we don't have data in between these data points, but we can say what was the average speed during these intervals by just taking the distance, which is, on the vertical axis is going to be 0.1 miles for each of these segments, and then divide that by the amount of time it takes, which depends on the specific interval in question. And, well, we get a value for each little segment of the data, and those are represented by these red data points on the bottom graph, and see how that lines up pretty nicely with the readings from the speedometer, indicating that the speedometer is doing a pretty good job of telling us what the average speed was during these intervals, even though it tells us our speed at a much shorter moment in time that is essentially instantaneous. And mathematically, again, instantaneous velocity means truly mathematically instantaneous, but the speedometer is telling us essentially the instantaneous velocity. And so it's pretty nice that those line up. It indicates that our procedure of getting the average velocity is not too shabby, and our idealization of an average velocity for the whole thing isn't too shabby either, because see how the data points don't go too far above or below that line. But what if we could do even better and get that line a little bit closer to the data points? Well, we could shift to doing something else where instead of just drawing a line from the first point to the last point, we ask the computer to draw us a line that gets as close as possible to all the data points. And it does this by saying that we're going a little bit faster than we really were, but started a little bit behind the actual start line. And that might seem a little bit strange, but that's actually the better way to come up with a mathematical model of the world, at least if we're going to approximate this as me driving at a constant speed instead of looking at this, more accurate representation on the bottom of showing how the speed, goes up and down as a function of time a little bit. And so this horizontal dashed line is just, well, what if we take, 36 and, plot a horizontal line at 36, because, go up, here's 30, here's 40, there's 36, and indeed, it's, pretty much in the middle of all of these speeds, which is what you'd expect. And so, well, like I said, each one of these little intervals can be divvied up, and we can get the average speed, and that kind of lets us get a handle on what's going on in between, right? Because I keep talking about it because it's important. We want to do two things, which are interpolate and extrapolate. And so if you want to know where I was, halfway between some of these data points, well, you could just, assume the speed is constant and multiply by the relevant amount of time and figure out where I was. So, note that these little orange lines here are just so you can visualize that a little bit better and see that there's this, sort of see this little triangle, right, where, horizontal component is, the long horizontal component is time, vertical component is the distance, and, so sort of, shallower angle triangle here is, slower speed, steeper angle triangle here, higher speed corresponding to higher and lower average interval speeds on this lower graph. And then if we just zoom in so you can see that a little bit better. Okay, so that pretty well covers our scenario of constant speed / constant velocity. But now let's start asking questions about models of a non-constant speed or a non-constant velocity. And I think I gave a wonky definition a while back of velocity, but it is going to make sense, where I said it was, moving towards or away from some particular point, versus speed is just your speed along the ground. And there's speed and velocity, and there's average and instantaneous. And so when it comes to instantaneous, velocity is just speed with direction. But when you start talking about, averages, that actually makes it weirder, because, velocity is how fast are you going in a particular direction, right? Up, down, north, south, east, west, what have you. And speed is just how fast are you going. And it's because it's a vector quantity, which we'll go over next week. Or, next time I do this, since this is not a formal course, although I wish I were teaching one. But for now, we're just going to introduce the idea that there's direction of positive, which is up, and negative, which is down. And we're going to look at a scenario where the velocity is changing in a predictable manner. Because in this situation, which, see, you can graph it by hand, and I did, our speed, and our average speed, is obviously not constant, but it's changing in a somewhat unpredictable manner that has to do with just, when there was traffic ahead of and behind me. And I just used that to show how you deal with a scenario where there's noise in your data and life ain't so simple. But then we can idealize it like this, right, where it's just, a straight line in distance versus time and a straight horizontal line in speed/velocity versus time. But remember, I said we want to be able to both interpolate and extrapolate what will happen in time. And if all we want to do is interpolate, well, there's kind of no drama, right? We just, look in between these two data points and say, okay, well, probably I was, just approximate the speed in each of these little intervals as, constant and equal to whatever the average given by, these averages are, and then say, okay, what point in time do you want? Take the, start point of the line, take the start point of one little line segment, one little line segment, multiply that by take the start point for one little line segment, add the amount of time since that start point, multiply that by the average velocity during that segment. That's how you can interpolate and pretty well guess the position in between data points as a function of time. But what about extrapolation? Well, you could extrapolate out using some idealization of just, a times x, or, speed times time. And, well, that might work okay, but only if it really is constant speed. Like if I was driving on the freeway and the only thing, controlling my speed was just not exceeding the speed limit and there was no traffic, that would be a pretty good model. But let's start thinking, let's look for a situation where the speed and velocity are changing and they're changing in a predictable manner, and let's go to the next simplest model after a straight line, which is, instead of, y equals a times x, how about y equals a times x squared, or times t squared for time squared. So, well, let's look at a situation where that happens. Okay, so what's all this? Well, it's me preparing to drop a little doohickey, but you'll notice that little doohickey, which is just some little magnet toys attached to the end of a string so that I can release them easily, are up against a background with markings every 10 centimeters. And so what that will let us do is determine how far it has fallen as a function of time. How do we determine the time? Well, with the magic of the video camera, which is recording at 240 frames per second, which is what standard smartphone can do these days. And every frame, therefore, is going to last 4 milliseconds. And by using some software to extract out the frames, which I'll make available, they can be labeled as a function of time. And I've also even put this counter up here so you can see how many milliseconds, or how many, it's just listed in seconds, but, count 3 decimal places down to get milliseconds. And we can see how long it takes to reach each marking, or we can see how far it's gone in each frame. And we can get position as a function of time and see how we can model that mathematically. So without further ado, let's go ahead and watch it fall. In slow motion, of course. And see, it starts to pick up speed. About halfway down, but almost out of time already. And boom. And it cuts off before it hits the ground because well, it makes it more convenient to extract the position as a function of time using the computer vision software that I'm using. But you can also do it by hand, and as always, I would encourage that as an exercise. So let's take a look at the data when we plot the position of that little doohickey as a function of time. Okay, so this is what it looks like if you measure the position of that falling object at 14 different points in time. And you can do this by hand, or I'll make the code available so that if you want to download the Open Computer Vision library for Python, you can run my Python code that will extract this. And so notice how this just looks like, well, not a straight line, obviously, but it still has a relatively simple shape to it because it sort of, well, is a parabola, spoiler. And so, like I said previously, we could ask the computer to generate a mathematical model that gets as close as possible to all of these data points, and we can tell it that we want that mathematical model to be a parabola, so something proportional to time squared. And so remember, a parabola has three terms, the independent variable squared, independent variable, and a constant. So it says that the model is 4.7 meters per second squared times time squared plus 0.17 meters per second times time, and plus, 1 millimeter of offset. And so, that's, again, an idealization, and it's not too shabby of one, though, and you can see it's pretty much hitting all the data points. And so, okay, now let's, ask ourselves the next question, which is, what about sort of average velocities, right? We could do our same procedure from before, where we can take each interval in time, and we can then we can measure, how far has the object fallen during that interval in time, and we're getting negative numbers because we're defining positive to be up and negative to be down. So it's, nothing dramatic is going on, with the negative numbers. It's just, we want to sort of, it seems logical to me that if the object is falling down, we should have our curve down like this. And it makes things a little bit simpler to remember. But you could do the same thing, modeling it with, positive numbers, but you just need to be careful to keep track of everything. And you would have to remember that negative is up and positive is down, versus this way, positive is up and negative is down. But we do, and so we get this negative number of minus 4.7 meters per second squared times the time squared to get the distance. So what if we just take, each of these little, distances, so some, take this distance, negative point whatever meters that it falls, divided by whatever this time interval is, which is, like, I don't know, it's 0.6 divided by 14. I can't do that math in my head right now, but it's some short little time interval, right? And, well, we get that something that looks like this, right? So just like before, each one of these dots is representing the average velocity during one of these intervals, and it's becoming increasingly negative because the object is falling down faster and faster. So it's starting at 0 and ending at about minus 4.5 here. And so we can again ask the computer to plot a line that's as close as possible to all these data points, but this time we tell it we want a straight line because, well, these look like they are lying pretty much on a straight line now, right? And the computer tells us that that line has a slope of negative 9.4 meters per second squared times time, right? Because this is, velocity in meters per second, so, it's meters per second squared times time in seconds gives us meters per second again, which is units of velocity. And up here, it's meters per second squared times time squared gives us units of distance. So, all right, that's pretty cool because, well, like I said, we're trying to come up with mathematical models of reality, and they are idealizations, and we want to think about them, but be aware of the fact that the real world is kind of noisy and messy like this, and aware of the fact that it doesn't necessarily exactly follow our mathematical models, whilst still learning to leverage them to better our understanding. So let's switch into math mode for a minute here, and let's consider an idealization of a parabola, or that, let's just consider a parabola as an idealization. And let's ask ourselves, what is the average change over each, interval 1 in x of the function, y of, f of x equals y equals x squared? Well, 1 squared is 1, so from 0 to 1 it increases by 1. Okay, so then from 1 to 2, we get 2 squared is 4, so subtract where we started, which was at 1, so 4 minus 1 is 3, again, just dividing by, how far we have gone in x, which is 1, and same thing again between 2 and 3, 3 squared, x squared, is 9, minus where we started, which was at 4, 2 squared is going to be, 5, again, same interval of 1, and we keep doing that, 4 squared is 16, minus 3 squared is 9, we get 7. And so, on and on and on. And notice we are just getting a nice simple pattern here, 1, 3, 5, 7, 9. And so, you might remember from last time, I told you that how to take the derivative of y equals x squared. And notice that if we do it this way, for a parabola, we don't even have to necessarily shrink our interval all the way to 0. In fact, the rule works with a parabola even for, large distances. So, notice that 1 is equal to 2 times 0.5, 3 is equal to 2 times 1.5, 5 is equal to 2 times 2.5, and, so it's just 2 times the midpoint value of the interval where you want to know the average change, right? And remember, the d by dx of x squared, the derivative, is just equal to 2 times x. So now let's go back to the data, but now instead of just extracting 14 data points the way you could by hand, let's do it for all 137 frames of the video, which gives us a much larger data set, and this you couldn't realistically do by hand, but I'll make the code available to extract the position using computer vision, and I'll also just provide a CSV file that has all of these positions as a function of time, or all the position values with the corresponding time values in a CSV file, which is, nice, universal, easy to read file format. And, or I should say, easy to work with using other programs. It's not necessarily, although it's not super challenging for a human to read. It's just, the numbers separated by commas. Although it is a little bit, it's not very visually pleasing, but it's, low overhead to get started with. So, but, now we have a lot more data points, but we still have a parabola, right? So now we're going to do the same thing. We're going to ask the computer to fit this with a, something that is proportional to time squared. And again, we're going to get something proportional, which is equal to, 9.7 times time squared. And now we're going to do the same procedure, and I'll show you why mathematical idealizations, even though they're not real, start to get very useful. Which is, let's look at the average velocity at during each one of these little intervals. And so now we're using a much shorter time interval. So you might think, oh, that'll make it, so that it's simpler. Well, it makes it really noisy, right? Because you notice how there's all these little jumps up and down here, because, we're no longer averaging over a long interval in time. We're, getting the position at every little moment in time, and the computer makes little mistakes here and there, and also there's just, it's a little bit blurry because it is, moving frame to frame, and it gets really difficult, and because we're not smoothing it out and averaging it over longer periods of time, it makes it really noisy, but we can still ask the computer to fit this to a straight line, and it still gives us, something pretty decent, which is, about 9.4 meters per second squared times the time gives us the velocity. But, plus or minus quite a wide error range here. But remember, though, that we would expect the slope in any interval, or the average velocity in an interval, to be proportional to 2 times the distance, right? And so the slope of this straight line, this coefficient is exactly equal to twice the coefficient for this, right? Which is what we'd expect from this equation, which is, pretty nice. So it's starting to look like it's not all made up after all. But so finally, let's sort of zoom in on our data and on our mathematical idealization. Because remember, last lecture I talked about how we do the derivative proper by zooming in on the function and looking at a shorter and shorter interval. And our data might have noise, but our mathematical idealization does not, right? Notice how it's just this smooth red line. And so it's made up, but it's nice and smooth. And going forward, we're going to start making a critical assumption, which is that all of the functions that we use to model the world are like this, which is a way of saying they're not going to be like fractals where you keep zooming in and they still have some like bumpiness to them. We're going to make the assumption that the more we zoom in on a function, the more it is just a simple line. And our data has noise, but our mathematical function does not. But you'll notice how they both kind of look like a straight line at this scale, versus if you zoom out like this, the red line is smooth, but it's not straight. And the data is neither smooth nor straight. And here, the data has noise, but it seems to fall along this line that's getting closer to straight. And of course, the red line is, a mathematical idealization, so of course it's smooth, and it's getting closer to straight. And so this green line is a perfectly straight line that I've just drawn on here. And, well, what if we zoom in some more? Because that's what I'm obsessed with. Well, our green line, that's just a straight line, is now closer to approximating the red curve, which is smooth, and our data still has noise, but it also is getting closer to just being a straight line. So if we zoom in some more, guess what? It gets even closer. And again, our data still has noise, but also gets closer. And if we zoom in some more, well, again, closer. And, well, we shouldn't be surprised, because that's the assumption we're making, is that we can, if we zoom in enough on any mathematical function, it can be approximated by a straight line like this, and that's going to be critical for us as we go forward, that we're not dealing with anything that has some weird fractal structure or something like that. And our data, correspondingly, if we zoom in enough, will just look like, whatever will also just look like a straight line plus some noise, but our data has some finite interval to it, right? And so that means that we might not necessarily be able to zoom in enough on our data to get it to the point where it can be approximated by a straight line, but we can always zoom in on our idealization. And so taking the difference between data points, like I was describing, and getting like the average velocity, that's called taking the finite difference, versus doing this mathematical calculation like this is actually called taking the derivative. And so doing finite differences is actually a really important thing if you want to be any sort of scientist or engineer. Even if you want to be a theorist, it's important to know how to take finite differences from things like numerical calculations. So, yeah, that's going to be crucial going forward. And again, we can zoom in more and more and more, and it'll get closer and closer and closer to a straight line. So, that's what it looks like mathematically when you let something increase its speed slash velocity at a constant rate, is you get a parabola. And next time I'm going to start talking about something else called integral calculus, because I'm apparently want to introduce things the way that I originally learned about them, which was to learn physics and calculus as one self-study subject. And this is kind of how I learned it. I learned what a derivative was by learning about average and instantaneous velocity, and I guess I just want to reminisce about that whilst hopefully providing something useful and maybe giving myself a leg up on getting actual chance to teach for real. But next time I want to go over integral calculus, and then next time we're going to have to introduce several complexities at once, but c'est la vie, maybe it'll get better organized in the future. So next time we're going to go over how to do integral calculus, so how to go from a, graph of velocity, changing at a constant rate, to something like this that shows the position as a result of knowing the velocity as a function of time. And then start going over some functions where you can't get away with doing the derivative with a, large interval. You actually do have to do this procedure of shrinking the distance down to 0 and relying on the fact that you can always go further and further in on a number line and never run out of numbers. And then we're also going to go over in the same lecture there, going to go over the actual statement of Newton's laws, which is going to add some further complexity, because this whole time I've been saying in physics we measure three quantities, which are, we measure length with length references, we measure time with time references, and now we're going to learn to measure mass with weight references, like this rock. So, well, like I said, this is going to be a circular buffer, so if I paint myself into a corner, I will just fix it on the next roll around, although I'll leave the old ones up, and I'm going to make the slides as well as the data and the code available, although, again, you can always do things by hand, but it starts to get real tedious real fast, and it's a valuable skill to know how to process and analyze data using programming languages and programs. So, anyways, bye.